So good morning, friends. I'm Professor N.V.S.N. Sharma, working in NIT Warangal. I did masters in this particular area of microwave and radar engineering from Indian Institute of Technology, Kharagpur. Then I worked for some time in Tata Institute of Fundamental Research on radar systems. Later on, I worked for my PhD in the area of microwave engineering from again Indian Institute of Technology, Kharagpur, and I joined this institute about 20 years ago, that is in 1990, and I have been teaching this subject right from first semester till now, and I have been also associated with the defense labs in Hyderabad in their radar jamming techniques projects. So with this confidence, I developed this course on radar engineering, and in today's class, I am going to give you the overview of this subject. So let us see what is that we are going to get after studying this subject. We will understand what is a radar, what are its applications, what are the frequencies used, what are the operational features of this radar. Then can we develop an equation for the operation of this system? After that, we are going to see different types of radars and their variations. There are limitations, benefits, advantages and other things. So let us get into the game of this radar engineering. So in this radar engineering, we will see a transmitter and a receiver being placed next to each other, and it can do the job for us. What is the job it can do? This is mainly to detect the objects. Metallic bodies can be detected from a far off location. What are the possible metallic objects in this context? They can be aircrafts, ships, cycles, or even human beings. These ones are having the capability to reflect or to scatter the electromagnetic waves impinged on them. So, early 1940s, people started experimenting on the scattering capabilities of these metallic objects, and from the scattered signals, people started making some measurements to see that whether we can make a system to observe these scattered signals. That is how slowly by 1945, during World War time, many countries could develop a radar system and make use of it. So radar was basically a military system to start with, to identify the incoming ships or aircrafts. And it is possible to detect the presence of a ship at a very far off distance. That was the advantage people could derive from this system. So the main objective of this radar system is to detect the presence of an object. For this purpose, we make use of electromagnetic waves. But the other name for electromagnetic waves is radio waves. So this detection process, we call it as radio detection. Not only the presence of an object we can detect, we can also find the speed of the object if it is moving. This gives a great advantage for the military people to understand what is the likely time of this object to enter into our boundary or territory, and what is the time I should fire the gun to eliminate this. That is how people could get a lot of advantage with the development of radar system during Second World War. Germans, British, US and many other countries could develop these things at that point of time. So Presently, the radar is not only a military system, but also is being used in many other fields. For example, the police people can use it on the highways to find out the speeding vehicles. The motor is going at speeds beyond the limits specified for that particular location, without the driver being observed or without the driver aware of that his velocity is being measured. That's the greatest advantage people could derive directly from this. Another major application people are taking the advantage of these radars will be in the area of maps, drawing the maps of the locations. From the satellites, we try to send these signals and get back the reflections to identify the location or to be able to give the map of a particular scenario. So this is possible by a special kind of radar called synthetic aperture radar, SAR. Okay. For the same applications, there are other ways people also try to do it, like sending the aircrafts or helicopters and other places to map a particular location, whether there are any ponds or rivers, mountains, or what sort of buildings and other things are there, we can find out in the present day. So like this, there are several civilian applications of these radars also. Here, what we are going to see is the reflected signal from the expected object will be the most useful part of the entire system. This reflected signal is known as the echo, and this echo will be processed in the receiver kept next to the transmitter, and we get the indication of the target in terms of its location or distance and even the shape, but not the color. If you are interested in the speed, we also try to measure its speed by finding out the Doppler shift in the return signal. This Doppler shift is a known phenomenon in the transmitter and receivers when they are moving. We know in our earlier subjects that whenever there is a movement between transmitter and receiver, there is a change of frequency in the received signal depending on the movement. So, if you observe the change in the received signal frequency, that gives an indication of the speed. So, this is being exploited in the context of these radars to find out the velocity of the target. So, the main points we are going to find here will be the echo and the Doppler shift. What exactly is that echo we mean? When did we come across this? This word we came across when we studied the subject of sound. When you stand at the top of a well and give a word, what happens? You will get the resound of that after certain amount of dip. Why does it happen? It happens because the sound signal goes up to the bottom of the well and gets reflected from there and comes back. So due to this, there is a delay in the resound or echo of this. So if you can find the delay in terms of the time, we can determine the depth of the well. That was the clue with which the radar systems could be started. So in this context, what I narrated just now, we are using the sound waves. Then, why we cannot use the sound waves in the context of radars? Why do we need to go for electromagnetic waves? The second one which we are going to see is the Doppler shift. So here, suppose there are two people on the two edges of the road and a car is moving from one end of the road to another end, and the driver is giving the horn. What's going to happen? Just imagine. Just a minute, I'll just give you the picture again. There is a road. At one end there is one observer for us. There is another observer at this point. And the car is moving from here to here. And the driver is giving the horn. What do you observe? the driver observes the same frequency signal at all the time. Yes or no? For the driver, he is moving with the same speed of the sound. So he doesn't find any change in the frequency. Whereas, for this person, what's going to happen? The vehicle is moving in this way or away from the observer. So he will see that the frequency of the signal is reducing. What happens to this observer? As the car is approaching him, the frequency of the signal is going to increase. This is what we call it as Doppler shift. For same frequency signal we are giving it all the time, but the driver who is moving with the same velocity is not observing any change in the frequency, but a person who is observing that it is moving away, there is a reduction in the frequency. For an observer who is getting the object close to him, there is an increase in the frequency. This is known as Doppler shift. So by determining the change in the frequency of the received signal, we can find out the velocity of the target. This is what exactly is being practiced in the case of radar systems. Another civilian application we find with these radars will be in the air traffic. Air traffic controller will be able to guide so many aircrafts approaching or going away from a particular airport only with the help of these radar systems. And another one is the meteorologists, the people who do research work on the weather. They make use of this to predict the weather conditions. There are radars who are meant only for identifying the weather conditions, or what we call them as weather radars. Weather radars also use the same principle of your Doppler shift. A simple Doppler frequency change can give you so many parameters of interest. It can give you velocity in one context, it can give you the weather information in some other context. It is all that from the return signal, what is that we are trying to extract, that matters. The return signal contains several informations, several ways you can make use of it to get the desired thing. So this radar is so interesting and having so many applications. It is purely electronic system. So when you study this subject of radar engineering, you will know how to design a system, how to conceive the components required for a particular operation, how to put them together and give a good architecture or system integration. You will come to know how to specify what should be the sub blocks of this particular system. How do I choose the characteristics of different subsystems or components or blocks or modules, whatever you call, you can identify with this. And also you can see how we can modify some of the blocks to get some specific applications in this radar system. Though a radar can do many jobs, sometimes you require only less number of jobs. So for that, how to design, how to maximize the performance, you can understand in this. That is why this subject is normally given in the 4th year or the last subjects of the entire program, so that you will be ready to use these concepts or principles in other areas also to design systems. So the basics of all the previous subjects will be made use of in this subject as well. Like we are going to touch some concepts of your circuits, ICs, microprocessors, communication theory, signal processing, microwave engineering, antenna engineering, similarly several others. So this encompasses all your earlier subjects. That is how you will have more confidence in those subjects, as you could see the application of those things in this particular area very clearly. So that is another added advantage of this. Then coming back to the system operation, as I mentioned to you, we are sending the waves towards the object and getting the echo from that. Then why we cannot use the sound waves? Why should we go for electromagnetic waves? If you go for sound waves, what's going to happen? It is going to disturb the neighbors, because they also can hear whatever signals you want to transmit and receive. And the echo from the sound waves will be very, very faint, very, very small value, which is very difficult to operate in the receivers. And the speed is also very less, like 3 into 10 power 2 meters per second. But if you go for electromagnetic waves, what's going to happen? The speed is very high, 3 into 10 power 8 meters per second. There is a change of 10 power 6. Is it not? So they travel at million times higher speed than sound waves. So if the target is hundreds of kilometers away, still you get back the echo within a very short time. Within some tens of milliseconds or even hundreds of milliseconds, you get the echo. That means you will get an indication of the incoming target when the target is hundreds of kilometers away, which is a great advantage for you to adjust the gun and see that you are ready. When it enters into your territory, you can easily eliminate. Am I right? And when you are sending the electromagnetic waves in a particular direction to observe the target and other things, you are not disturbing anybody. So the interference to other systems or neighbors is very less. The return signal is also considerably large, because the attenuation of the electromagnetic waves in the air or in the free space is comparatively much less. So you get good amount of return signal, wherein you find it very easy to process it in your receivers. That is how people have chosen electromagnetic waves to use in the radar systems for the identification of the targets. When electromagnetic waves are not possible, in which context? In the context of sending the waves under the sea for the detection of submarines, definitely we have to go with only sound waves. Electromagnetic waves cannot propagate in seawater, because seawater is a conductor. There is no choice of electromagnetic waves, we settle for sound waves. So in the context of submarine identification also, we use the same concepts and everything. The only change is, instead of electromagnetic waves, we use sound waves, and we call such a system as sonar. So radar and sonar work on the similar principles. Okay. Now the invention of this radar, can you imagine how did it happen? It is James Watson Watt who just took some paper and put a block diagram that we need a transmitter, we need an antenna to radiate the signals, and we need another antenna to receive the signals, and a receiver to process the received signal to get the indication. With a simple block diagram, he has established initially that there is a system possible to identify the incoming targets, to detect by radio means the presence of a target, and also the distance at which it is at this time. That is what we call it as ranging. So ranging and radio detection are the two jobs which we are doing with this system. So the words what we have mentioned so far are put into a short form: radio detection and ranging. So RADAR are put together to call this as a radar. So radars are many varieties, or there is a good classification that is possible. What is that? The classification is by the types of operation. Till now I was mentioning that we keep a transmitter and a receiver next to each other, radiate from the transmitter, receive through the receiver, and process it. If you are keeping it like this, that means a transmitter and a receiver next to each other, when you keep it, then we call it as monostatic operation. At one location, everything is going on. This is normal radar operation. But there is a way now which is coming up that we keep transmitter at one location, receiver at another location. That's what we call it as bistatic radar. Two different positions we are using, and there are many varieties that are possible these days, that we are going to have a radar network. What is that? We send from one single transmitter, receive the signal through different receivers, which is very useful. So from the different received signals, we try to get many details, many more details. That is what is being developed nowadays. So radar network is what people are contemplating. Like your computer networks or data networks, ad hoc networks, sensor networks. We have now the other side of the radar system that is happening is radar networks. We are not going into such a detail. So by operation you can say, if you keep radar transmitter and receiver at the same location, we call it as monostatic. If the radar transmitter and receiver are at two different locations, then we call it as bistatic. This is one classification you can have. The other type of classification is that, are we using pulse signals or continuous wave signals? CW or pulse operation is another way. There is a third way people are talking about, is the coherent operation or non-coherent operation. Okay? There is one more variety, we call it by frequency band of operation. Radars operating in L band, operating in X band, radars operating in K band. Like this you can always try to identify. They will have similar characteristics. Okay, similar devices are being used. Okay, thereby we will have another classification possible with frequency bands also. So in this course on radar engineering, we are going to see what is the basic operation we are going to have. How do we send the signals? How do we generate them? How do we amplify them? And see that it has a specific nature, pulse shape or a continuous or something. You may ask me, are these the only types? It is not. In the recent past, people are attempting other waveforms also, like a Gaussian pulse or some arbitrary waveforms, which can give rise to some other advantages. The main problem in the radar operation is the noise from the environment. The signal is traveling through the environment up to the target, and from there it is again returned to the receiver. So there is so much corruption of the noise in the signal received. So we need very high powerful signal processing techniques in this. Here we call it as radar signal processing rather than your conventional digital signal processing. If you look at the pulse operation, it is the same thing we can do here also. We are sending a digital signal like a pulse and getting the distorted pulse as the received signal. So we have the same digital processing techniques in this context as well. Match filter, Kalman filter, etc. will be used here to improve the performance. The radar has become a reality after World War II, and initially they were used on the ships as a voluntary thing to add convenience to the pilots or the captain of the ship and other people. But as the ships became very large size and the ports have become crowded, when the ship is coming into the port, they found the use of the radar is quite immense, that slowly they made it compulsory for all the ships to have a radar system. At the same time, people developed the aircrafts, etc. So in that also they found the use of the radar is very high. Then they made it compulsory in the aircrafts also. But initially there was lot of resistance from the mariners to use the radar system, like as we found in our day-to-day life. Many people have hesitation to go onto the computer even now. Many people have hesitation to use a mobile phone. But as we see, without mobile phone, the life is nothing for many people already. So mobile has become a common thing. In the same sense, the radar also has become an inevitable component in all ships and aircrafts because of its immense use. In the case of radars, there are specialities we make use of. The distances are generally given in terms of nautical miles, NMI. 1 nautical mile is about 1.75 kilometers. A normal mile is 1.5, is it not, kilometers, whereas here it is 1.75. So when we are talking to a radar engineer, first of all we should change our language to nautical miles. Similarly, the display of the return signal is normally not on a CRO as it is. A CRO gives voltage to time indication. Okay, in the good olden days we used to have such devices called A-scopes, the return signal amplitude versus the time of return. But slowly people found that there is a different way of representation that is more convenient, and they landed at a different scope called PPI, plan position indicator. So like this, there are definitely some more new things which you will be coming across in the subject of radars. Similarly, the velocity of a target is not given as meters per second or kilometers per second. It is expressed in terms of knots, KNOT. Okay, 1 knot is equal to 300 meters per second. Okay, velocity of sound, minimum value is 1. Multiples of that is 2 knots, 3 knots, 4 knots, like that. So here the people could find that the ship, when it is entering into the port, how to control different operations and see that there is no collision with other ships or other lower level boats, trawlers and other vehicles that are there across this. Similarly, at the airport, the ATC will find it very convenient to use a radar to see that there is safe landing, and from the landing point up to the airport location, wherever it is supposed to be parked, they can guide the aircraft very conveniently like this. And slowly people made use of this radar even under poor visibility conditions. When there is poor visibility, the ATC will be able to see that the landing is very safe by giving proper signals to the pilot or completely controlling from the control room itself. That was the advantage we have, or here we call it as GCA, ground controlled approach, is completely possible with these things. So with the radar systems introduction, the ships had lot of convenience at the ports, and the collisions were almost avoided by this. The same has been extended to the case of aircrafts also at a later stage. For the navigation, when we use these things, we call these devices as navigational aids. Here we have some slides representing how exactly it looks, the radar display unit. The output of the receiver is displayed on different scope, a circular scope or a polar chart type of thing, where range versus azimuth angle is mentioned in certain cases, range versus elevation is indicated in certain other cases. So these are the ones which you are seeing on the screens here. By the advantage of these radars, even if there are two targets coming one after the other, you will be able to discriminate. Or two targets coming at close angles, you will be able to discriminate them and clearly identify that you are getting two targets. So these are some of the cases what we have in the subject of radar engineering. Now let us get on to the topics which we are going to see in this radar system. The topics will be one thing on what is a radar, how is it built, what are the blocks we need to combine to get it operational, and what information we are going to get, what is the signal we are going to use. So these basic things will be given in the subject of radar basics. Okay, and a typical radar specifications are like this. If you want to design, these must be known first, that what is the power we expect, what is the horizontal beam width of the antenna, what is the pulse width we want for this, what is the pulse repetition frequency, and what is the noise figure of the receiver. Like this, we first identify what are the values we expect for this radar. Then we identify what type of transmitter must be used, what is the receiver, what is the antenna, or whether we need two antennas. All these things will be calculated, and then we go for the movement, how much is required for the antenna to identify the targets coming in different directions. So all these specifications will be put together to identify what sort of transmitter blocks can do for us, what type of antenna is required, what type of receiver is to be designed for this purpose. So taking all these things, we go step by step in the radar basics to radar equation lecture. In radar equation case, we are going to develop an equation with which we can identify the changes in the inputs that are possible and the output values that are going to be affected by this. That means, how is the range performance of the antenna getting changed due to changes in the transmitter power, or antenna size, or frequency of operation, or receiver noise figure, all these things. So range equation will give you a control on the entire operation of the radar system in any general case. Then we modify this range equation for the specific cases. For example, in the case of distance measuring equipment used on the aircrafts to know the height of the aircraft above the ground, what is the change we need to do in the design, why we need to do, you will get the idea from that discussion. So radar equation topic is very crucial for all the engineering students in this. It gives you the complete insight of the entire subject. Then we proceed on to the case of a variation in the basic radar operation. That is, instead of using CW, what is going to happen if we use a continuous wave signal? That is CW radar, wherein we use the Doppler shift as the key for entire operation. So this is also known as Doppler radar. Here we will understand what are the blocks required to operate a CW radar, what are the equations by which we can get the final parameter of interest, that is the velocity, and what is the limitation. The main limitation in this will be that it will not be able to give you the range value. So to get that range, we modify the system. We add modulation to the continuous wave signal. See, the communication background is useful in this context to see that we are getting a different parameter of interest by utilizing those concepts. So frequency modulation is applied on continuous wave signals to get the range information. The system, we call it as FMCW radar. So we are going to see in depth how we get this. That is, why frequency modulation, why only frequency modulation, and with that frequency modulation, how much we should do to get a good range information. So these are all the details we are going to see in the context of FMCW radar. That is the second lecture for us. Then we move on to the different types of radars. That is, one is MTI, moving target indicator, and the variant of this is the pulse Doppler radar. We will study both the topics together because the systems are same, only the operation is going to be slightly different. In the case of moving target indicator, we get indication of the moving objects. The stationary objects will be deleted. So for that, what additional circuits are required? And how do we design that circuit? That is, delay line canceller is the extra component we require for this, and how to design such a delay line canceller we are going to see in this. when it comes to pulse Doppler radar, it will not be able to give you a good information on the position of the target, but it will give you an accurate information on the velocity of the target from the same system. So pulse Doppler has some advantages, whereas MTI has some other advantages, and both cannot be met by the same system. That means they follow Heisenberg's uncertainty principle. So this is all that we are going to understand in the third lecture on MTI and PDR. Then we move on to tracking radar, that is, how do we get the continuous information of the incoming target. We are not interested in any other things, we are interested only about a particular object and how it is approaching the radar system. That is what we want to track. So for this, what are the conventional systems and what are the present day systems? Conventionally, we have been using conical scan. So we will study that, what are its limitations, what are the disadvantages we get, and how it can be jammed easily. That information also will be presented in this. So to beat all these things, what is the modification that has been suggested, and how do we get all the informations from a single pulse? That is what we call as a monopulse, we are going to see in this. And monopulse, the latest variety is the two-dimensional monopulse, we are going to see in this. What are its advantages and other details. So after this, we will concentrate on the system design of the radar. How do we identify the sub-blocks, or what components, what systems, what networks, what circuits are required for the transmitter, and what are the things we require in a receiver, what are the variations we can introduce in the receiver for different applications. So entire transmitter design, receiver design, types of displays, types of antennas to be used specifically for radar application. In that also some specific cases like constant altitude targets, if you are getting like a normal aircraft reaching an airport, why we need a special antenna pattern for that, you are going to see in the topic of radar transmitters and receivers. So with this, you will get a very good idea of system design, system integration, system specifications. How do we break that into sub-block specifications or component level specifications? This sort of development will come in you to design systems after studying all the details of this. Then we study the latest topic of these radars, that is the phased array radars, or otherwise known as electronic scanning radars. What is its speciality? How is it able to give you so many things in one go, and what are the parameters by which it is becoming so costly? So these details you are going to see in the topic of phased array radars. So with this, we study the primary radar systems and their plus and minus points, what are the varieties, applications, and many more things. Then we will go to the last topic, that is on navigational aids. The modified forms of the radars are being used in the navigation for the ships as well as for the aircrafts in different ways, in different frequencies. So those ones like a VHF Omni range, distance measuring equipment, instrument landing system, and other things like automatic direction finder, you are going to understand in the topic of navigational aids. So with this, we are going to complete all the topics required for an undergraduate course in radar engineering at various universities. We are doing it in a free space and there will be some amount of inaccuracy. It is not that you are going by a tape. You are measuring by some optical means or electromagnetic means. So when you say the distance is 53 kilometers, it is not exactly 53.000. It is 52.990 or 53.010 or something like this. Some error is there with that. That much is okay. That's why we call it as an approximate or quasi value. It's not exact value. That's why we call it as range. So range, if you want, you have to integrate the velocity. That is not possible in this context. You are doing on a continuous basis. So This is one reason we put it. The other reason is that if you want range information, anytime, range is distance basically. Distance, how do we get? Velocity into time. Velocity is fixed in the free space. So what is the time? The signal is sent from the transmitter, goes up to the target and comes back. So if you measure this time into velocity divided by 2 gives you the range. That is the basic equation. That is how the pulse, when you send, you start your counter, send the pulse, gets scattered at the target, it comes back. A small fraction only comes back. It is not true reflection. Reflection means it goes and comes back. No. It goes, the object acts like a reflector, scatterer. Only small portion comes towards the receiver, that will be received, and the time, if you measure, 2 times the range it is. So C into time divided by 2 gives you the distance. When you go to the continuous wave signals, you are sending the signal continuously. So when you have sent this particular received signal from the transmitter, you never know. In the case of pulse, you know, you have sent and started the clock and you have received. CW signal, when did you send? So there is no timing mark in the received signal when it has been sent. So you cannot measure the range. If you introduce the timing mark, that is by modulation. What is that we are doing in FM? We are sending different frequency signals at different times. So if the received signal frequency is this, transmitted signal of this is at that particular time, when you note it down, I am sending the signals between 100 megahertz to 200 megahertz. 150 megahertz is that I am trying to identify. So 150 megahertz I will see when it is sent, my clock starts, it goes. 150 megahertz when it is received, I stop my clock. I can find the time. Is it not? Or I put my clock for 120 megahertz. 100 to 200 megahertz I am changing, or 100 milliseconds time. Go to 200, come back, again 100 to 200, come back, 100 to 200, like this. You need not do all that also. You have the convenience at the expense of inaccuracy in the measurement. Obviously, you can use these things. And you need not go in a triangular manner like this. You can go in sinusoidal and other aspects also. What is that? You are giving the input signal for FM. A triangular signal. Is it not? Or a sawtooth, whatever we call it. You need not give that also. You can give a simple signal, but with inaccuracy. This is what the electronics part you are going to see more and more details when you go to the subject.